Now here are two more examples of finding limits. Let's look at the first one, which is number 44. Limit of the function is 1 over radical 3 minus 2x squared as x approaches 1. Remember, when we find limits, the first thing that we always need to try is plugging in the number. And by plugging in the number, what we are checking is that the function is continuous at that point. So if we plug it in, so let's just plug in the number 1 over radical 3 minus 2 times 1 squared. So when we plug it in, we get 1 over square root of 3 minus 2, which is equal to 1 over radical 1, which is 1. So this tells us that the function is continuous at x equals 1, and the limit is equal to the value of the function. So that's our limit. So if substitution works, then that's where the problem ends. So we find the limit by substitution. Now let's do the next one. Substitute x equals 0. Let's try that first. That'll tell us whether the function is defined at that point or not. So we have 25 plus 0 inside the radical sign over 2 times 0. So in the numerator we have 5 minus radical 25 over 0. 5 minus 5, because radical 25 square root of 25 is 5, and that's 0 over 0. So obviously substitution hasn't worked, but if you have a 0 over 0, we still have hope that we'll be able to find a limit. So there is one technique we could try, and that is multiplying and dividing the numerator or the expression with the rationalizing factor of the radical expression. So the radical expression sits in the numerator. Its rationalizing factor is 5. The minus becomes plus square root of 25 plus x squared. The whole divided by 2x squared times, so since we've introduced this expression, we need to do the exact same thing in the denominator as well. So we have 5 plus radical 25 plus x squared. So this is equal to limit as x approaches 0. If we have a plus b times a minus b, we have a difference of squares. Square the first minus square the second. That's exactly the form that you see. A minus b times a plus b. So we have the square of the first minus the square of the second divided by whatever we have there, which is 2x squared times 5 plus radical 25 plus x squared. Now this is equal to the limit as x approaches 0 of 5 squared, which is 25, minus, remember the square and the radical, so if you have radical x the whole squared, it's equal to x. So that would be minus, so that's really absolute value of x, but if we know x is positive, just leave it as x. So that would be minus, in parentheses, 25 plus x squared divided by 2x squared times 5 plus radical 25 plus x squared. So that is equal to the limit as x approaches 0, 25 minus 25 minus x squared divided by 2x squared times 5 plus radical 25 plus x squared. So this is equal to limit as x approaches 0, 25 minus 25 is cancelled, negative x squared divided by 2x squared times 5 plus radical 25 plus x squared, close parentheses, and this is equal to limit as x approaches 0. Now cancel the x squareds. You have -1 in the numerator over 2 times 5 plus radical 25 plus x squared. Now what was causing the 0 in the numerator and the 0 in the denominator was really x squared. Since x is approaching 0, we were able to cancel the x squareds, and now we are ready to plug x equals 0 back into the expression and see if we get an answer, which is the limit, which is square root of 25 plus 0, so 0 squared. This is equal to -1 over 2 times 5 plus 5. So that is equal to square root of 25 is 5. That's how we got the 5 minus 1 over 2 times 10, which is -1 over 20. So here we got our limit, which is -1 over 20. But what really worked for us was multiplying and dividing by the rationalizing factor. So that's the technique that works. Multiplying and dividing by the rationalizing factor. What do we mean by the rationalizing factor? If radical A plus radical B is the radical expression, then its rationalizing factor is radical A minus radical B. And that's the technique that helped us cancel out the x squared that was causing the 0 in the numerator and the 0 in the denominator.